Hello everyone, welcome to this video. In this video, I'm going to be explaining exactly what port scanning is and what a port is, because before you can actually start interacting with ports, before you start talking about TCP, sending, specially crafted packets with, various TCP headers to particular ports and then awaiting responses, we actually need to understand what a port is, right? And how ports work in relation to the device or their host, and how you can communicate with a port, right? So let's in this particular video, I'm just going to be using a whiteboard just because it helps it helps explain things a whole lot simpler, right? So we have let's take a simple example, right? On your computer, let's say you have a computer. Every individual computer has ports, right? Now you can think of ports as particular services that you can run on that computer. So for example, if you wanted to run a web server, let's say you wanted to host a web server, that would run on port 80 or port 443. And that's how people would be able to access your computer. Because remember, your computer has an IP address, right? And that is how this IP address is a unique identifier that allows everyone on the internet or specific people or specific individuals to find you. And if they open their browser and enter your IP address, so let's say your IP address is 192.168.1.1. So this is just a user who enters, this is their browser, and they enter your IP here, 168.1.1. What it's going to do is it's going to connect to your IP address, and it's going to connect to this particular port because this user here is requesting for the web page, and it does that typically through port 80 or port 443. So that's an example of a port. We have port 80. We have about 65,535 ports on a single device, and they both interact, and they all interact through two protocols, which we'll explore in this section. One of them is TCP and UDP, and these protocols essentially control how the connection is made to these ports and what the requests and responses can be like. However, for now, I just want you to ignore TCP and UDP, and let's just focus on the ports. So as I said, we have a total of 65,535 ports that can be run on a device or on a host or on a computer, whatever you want to call it. And you typically have the most common ports that are used for common services, as I said, like running a web server. So for example, starting from the smallest number going to the highest one, we can start naming a few of the most common ports. So for example, port 21 is FTP, that is your file transfer protocol. We will have a PDF in the resources section of this video to where you can download that, and that contains a list of all ports and the various services running on it. You can look at it as sort of a cheat sheet. So then you have port 22, which runs SSH, right, which is your secure shell. We have 23, which is Telnet. SSH replaced Telnet. You then have port 25, which is SMTP. That is your simple mail transfer protocol. And then after this, let's see, what do we have? We have something. Let's see, port. We have 53, which is DNS, right? DNS works on UDP. The rest of these work on TCP. And again, as I said, for now, just disregard the protocol that they use. So we have port 53, we have port 80, which I said is HTTP, and we can keep going on and on. And again, for example, let's just continue a little bit further. We have a port 110, which is POP3, which is your post office protocol, which is an email protocol similar to SMTP. You then have port 445, which is SMB, right? And we'll be taking a look at SMB enumeration later on during the course. We have tons of other other protocols that you can look at, and again, this will all be linked in the resources section. So again, going back to our earlier example, right? Every computer has a port, and it's a means of providing a service or hosting a service on that particular device. And you'll find that, for typical or standard computers, they also have various ports open based on, the vectors that they might be, or the services they might be providing. So for example, a web server would typically have a port 80 open or port 443 open for HTTPS connections. It would then have port 22, which is SSH, open for 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 remote connections into the box for management, and then it would have something like maybe SMB. It could also have FTP for transferring files through FTP, so it could also have FTP, so on and so forth, and it can have as many services as required. It could also be handling email, so 25 SMTP. And now these ports, when we're talking about ports usually have statuses, right? Or their current state. So a port, like as we saw with Nmap during the Nmap scan, we have the port, and then we have the state, and then we have the service, right? So we can look at it that way. So for example, let's say we have port 21. That is the state is open, right? So that means we can actually we can send requests to that port. We can initiate communication. We can then establish communication with a protocol like TCP. And we can also, we have established communication through that port. And this, again, as I said, is FTP. And then we have port 22, which is, we can say that's open as well. And that is SSH, right? And then maybe let's say we have, let's see, let me think of a interesting port here. Let's say we have port 80. Well, not port 80. Let's say we have port 23, which is telnet, and that can be closed, right? So we don't want to enable access to port 23, even though the service may be running. You can disable the service, but it could be still installed. So that is running telnet, and you get the idea. So what Nmap does is, if a device is running all of these services, what Nmap does is it sends a request to all the ports on the target, right? So it sends a request. So let's say we have we have a port here, we have a port here, another port, another port. So Nmap sends a request to that port, and then based on the response it gets from the port, Nmap is able to tell, hey, this port is open or closed. So in this case, we can say it's open if it gets a request. So let's say Nmap sends it again, and this time it doesn't get a response. So Nmap says, hey, that might be closed, so on and so forth. And of course, it gets much more complicated than this, but I just wanted to introduce you to the concept of a port if you don't have a good understanding of it already, before we start taking a look at the OSI model and the various the important layers, like the transport layer and the network layer. And then we'll start talking about the important protocols, which are TCP and UDP. And then we'll end up with taking a look at the TCP header flags, which are very important with Nmap. And yeah, that's primarily going to be the focus of this module. Very, very important module if you want to understand how Nmap works. So that's going to be it for this video, and I'll be seeing you in the next video. Hello everyone, welcome back. In this video, we're going to be taking a look at the OSI model. This is one of my favorite aspects of teaching networking, because this is where it all starts making sense. Right, now we've talked about ports. Now we need to start taking a look at the various protocols and like TCP and UDP. However, before we do that, we need to see where all of this stands in a grand scale, right? So we need to understand where TCP, UDP stands, where IP packets stand, so on and so forth. And this is where the OSI model comes into play, right? So the OSI model stands for the Open Systems Interconnection model, or if you include the suffix model. So this is a structured model, right, or a way of understanding that explains how networks work. That's exactly what it is. But how does it do this? It does this by sorting out the functionality of networking in the form of layers, right? So it layers functionality and the means of data transfer in the form of layers. And this helps many people conceptualize or understand networking much more easier, right? Because it's if you think about it, it's very vague, right? If you send, or if you load a web page on your browser, it's really difficult to understand how all of this is done directly from your motherboard all the way to your network interface card, all the way to your router, and then it goes into your ISP, so on and so forth. So that entire process is all explained very, very well with the OSI model. So as I said, it offers a great model or an idea of conceptualization of the to understand how networks work and how each layer communicates with each other to facilitate the transfer of data. Now, this, of course, can be explained by taking a look at it physically, so or using an illustration like this or a diagram. So I'll just take you through it, and already you'll start understanding how networking works just by taking a look at this model. So we have 7 layers in the OSI model. We have the physical, We have the data link layer, network layer, transport layer, session layer, presentation layer, and the application layer. The lowest layer here, which is the one you start with, is the physical layer, right? So the physical layer is where you're essentially dealing with, again, you're dealing with the physical structure, you're dealing with cabling, you're talking about coax, fiber optic, wireless, you're dealing with, hardware like hubs and repeaters. However, the important thing to take into consideration here is when you're talking about the physical layer, the mode or the means of transmission is in the form of bits, right? So that should be quite clear. So you're dealing with bits. You then move on to the data link layer, right? So the data link layer is where things start getting interesting. So this is where you're dealing with, your physical addressing, like your MAC addresses. And you can see we're now dealing, instead of with bits, we're now dealing with Ethernet frames, right? So we're primarily talking about Ethernet, and the transfer of data is in the form of frames. So you have your switches, bridges, and you're dealing with MAC addresses. So you're really just dealing with physical addressing of devices on the network. So, when you connect computers onto a network, the data link layer is where you're dealing with your MAC addresses and Ethernet frames. We then move on to the interesting layer, the most interesting layer, which is your network layer. And that's where we start dealing with packets, right? So the means of transmission here is now changed to packets, and you have your protocols like your IP, right? Your internet protocol. You then have ICMP, you have IPsec or IPsec, and IGMP, right? So the network layer, the purpose of the network layer is to facilitate, the transfer of data, from one host to another. So you're dealing with your path determination, and you're dealing with logical addressing of computers on a network, right? So instead of using MAC addresses alone, we now have IP addresses. You then have your transport layer, right? So your transport layer is you're now dealing with segments. Instead of packets, you're now dealing with segments, and your protocols here are TCP and UDP. So again, you can actually see we have that annotation here. You're dealing with end-to-end communications and connections. So that's why this is where you have your TCP protocol, which stands for your transmission control protocol, and then you have your user datagram protocol. So you're dealing with end-to-end connections here. You then have your session layer, which is again just between is interhost communication. It facilitates interhost communication. So that's where you have APIs, sockets, etc. Right. So in this case, or in this course, we're going to be focusing primarily with the transport and network layer, and that you can understand why we're dealing with packets and the communication protocols like TCP and UDP. You then have your presentation layer, right? So your presentation is just essentially its function is for data representation and encryption. So this is where you have you have protocols like SSL, you have SSH, IMAP, FTP, MPEG, JPEG, etc. And then you have your application layer, which is the topmost layer, and that's where you're dealing with your various protocols like HTTP, FTP, and this is the end user layer, right? So in our case, as we move along and we start talking about TCP, the TCP three-way handshake and the TCP header flags, we'll primarily be dealing with the transport layer. So I just wanted to go through the OSI model with you and explain what each layer does. As I said, this slide and this image will be available as a resource to this video, so you can go through it yourself. The purpose of this course is not to go through all the layers within the OSI model, or it's just to explain the importance of understanding it when using tools that utilize protocols like TCP and UDP. That being said, that is going to be it for this video, and I'll be seeing you in the next video. Hello everyone and welcome back. In this video, we're going to be talking about the network layer. Now, as I mentioned in the previous video, as we were talking about the OSI model, the network layer is very important to Nmap because we're primarily dealing with the internet protocol. So the function of the network layer is used for the transfer or the flow of packets across a network, and that's very important. And that's where we have our first protocol, which is the most important. That is our IP protocol, or the internet protocol as it's called. Now the internet protocol is very interesting because it has two versions. We have IPv4 and IPv6. IPv6 was supposed to replace IPv4 because we were eventually going to run out of enough addresses that we could use. However, we came up with NAT or NAT, or the network address translation, but that's besides the point. So the purpose of the internet protocol, or its function, is to specify the format of the packets and contains addressing information that enables packets to be routed. So it's essentially responsible for the routing of packets across a network. So it provides only the functions that are necessary to deliver a packet from a source to a destination over an interconnected system of networks. And you can remember from the previous video, IP is used for logical addressing, right? So it helps deliver data from one computer or one host to another, in an interconnected network. So it's very, very useful at sending data from one source to a destination very reliably. As I said, we have two protocol versions, IPv4 and IPv6. We're going to be focusing on IPv4 in this course, even though Nmap does have the ability or the functionality to scan IPv6 addresses and networks. So let's take a look at the IPv4 packet header, because this is where things start becoming interesting. And I'll be able to demonstrate this with a tool like Wireshark in a few seconds, when we'll actually see the header of the IPv4 packet, right? So the IPv4 protocol defines many different fields in the packet header. Let's take a look at some of these fields. All right, so one field is the IP source address. That makes sense. Every packet needs a source address. So this is again, this tells this essentially points out where this packet is coming from what device it's coming from. You then have the IP destination address, where this packet is going to, or its destination. You then have the time to live, or the TTL, which is an 8-bit value that indicates the remaining life of the packet. All right. Again, this can be used to calculate hops through. It can be used to calculate the amount of hops through a network and how many devices it's gone through. You then have the type of service, right? So the type of service, again, is an 8-bit binary value that is used to determine the priority of each packet. You then have the very important field here, which is the protocol field. So this is an 8-bit value that indicates the data payload type that the packet is carrying. So are you carrying TCP, UDP, etc. So this is these are the important fields you need to be aware of. Now this can actually be demonstrated live, and that's why I'm going to open up my virtual machine here, and boom, we are currently in Kali Linux, right? And I'm going to be using Wireshark to demonstrate this, right? And what I'm going to do is I'm going to run a simple Nmap scan, and I'm going to run it on my router, right? So I'm just going to say Nmap, and I will say F, or I can just say 192. I'll run a default scan, 192.168.1.1, and you can do this as well if you have Kali Linux set up. I'm essentially just demonstrating the IP or the IPv4 protocol and the header and the fields within it. So before I hit enter, I'm just going to fire up Wireshark here. So Wireshark is a traffic analyzer, if you're not aware of that, and I'm just going to run it, right? So, but before I do that, I'm just going to double click and run that, and I'm going to start the scan, right? And the scan ran, that was very, very quickly. If I now go back to Wireshark, you can see it's returned a bunch of results. However, the key here is not to focus on anything. You can just see that we have various columns here, and the most important thing that you want to look at right now is, of course, if we just go to the time here, and we look for a packet. So these are all packets being sent, and already you can see very important information in terms of the columns. You have the source, the destination, the protocol. But if we click on a packet here, and you can see I can click on a packet, and let me just enlarge this window here. You can see we have all the network layers that we saw in the OSI model. So we have the data link layer, we then have the network layer, and then we have the transport layer. So if we open the network layer, where we have the Internet Protocol version 4, we now have the fields. So if we go right at the bottom here, you can see we have the time to live. Remember that field? We then have the protocol field, which tells us this is a TCP packet, right? We then have the source and the destination address. So we can see the source address was my router, 192.168.1.1. We then have the destination address, which is my Kali Linux device, and that tells you that, hey, this packet was sent from the router to my device. So again, you can actually visualize the OSI model. We start off from the data link layer, and again, you can actually see this. It's in the form of bits. You then have your You have your network layer, which we have right over here, and which is right over here. And you then have your, your transport layer, etc., etc. So you can see it's very easy to visualize. And again, I can click on any other packet. I can look for the source address here from my device. So if we take a look at this one here, and let me just enlarge that back, and let me just minimize that. So again, we have the frame, the Ethernet frame here. And then we have our, if we take a look at IPv4 here, we can go ahead and take a look at all of the flags within the header. So we have the time to live, the protocol, which is TCP again, the source, destination, etc. And in the next video, we'll start taking a look at the transport layer, which is where we have protocols like the Transmission Control Protocol, or TCP, which has its own headers, which is again where Nmap starts becoming very, very interesting with the TCP flags like the SYN flag, the ACK flag, etc., etc. So that's going to be it for this video, and I'll be seeing you in the next video. Hello everyone, welcome back. In this video, we're going to be taking a look at the transport layer. Now, the transport layer is where things get very interesting, especially with Nmap, because we start talking about TCP, and we'll also take a look at UDP. So just going back to the OSI model, let me explain what the transport layer is and what it's responsible for. So the transport layer is used to facilitate end-to-end connections between hosts through the use of transmission protocols like TCP and UDP. Now, TCP and UDP are vastly different in how they actually transfer data. So let's talk about TCP and UDP. So firstly, with TCP, it stands for the Transmission Control Protocol. So this is a connection-based protocol. This is very important, and that's why we'll take a look at the TCP three-way handshake, because the TCP three-way handshake essentially establishes a connection between a host and another host, or the client and a server. And the reason for this is because TCP is used to transmit data reliably and in an orderly manner with the form of sequences. So again, TCP is usually combined with IP to actually give us the annotation or the notation TCP IP. And the reason for that is because data is sent with TCP reliably in that it's sent in sequences. So the data is sent in an orderly fashion. So again, it does this by establishing a three-way handshake. An example of where you typically find TCP being used is through loading web pages, where you want data to be sent in a sequential format as opposed to data just being sent without any particular order to it. So when we talk about the TCP header, what fields are we dealing with specifically? Well, we're dealing with the source port, the destination port, and TCP flags. Now, in this video, we'll not talk specifically about TCP flags because I want to cover that in the next video. But again, I'll demonstrate this all within Wireshark. So again, the source port essentially explains the port that this is coming from. The destination port, again, where this particular data is going to. When we talk about the UDP, or the User Datagram Protocol, this is a connectionless protocol that is used to transmit data in an unordered manner. And an example of this is, when you talk about low latency data transmission or communication, and as I said, an example of this is audio and video call. This is an example where, or this is a scenario where you want data to be sent without any real regard to the order in which it's sent. You want something that is sent really quickly. So a good analogy of this, as I said, is taking an example as we saw with TCP, that's used for transferring data in an orderly fashion. With UDP, you're essentially just sending data to the target in an unordered manner. And if you take a look at the header, you can see you only have the source port and the destination port, whereas with TCP you have the addition of TCP flags, which determine what you're trying to do, because as I said, with TCP you're dealing with a three-way handshake, and that's what we're going to take a look at when we start going through the TCP flags. But UDP is much simpler in that again, if you take a look at the header, you have the source and destination port, and why don't I just demonstrate that right now? So I will just open up my VM here, and again, we'll use the same example. We'll go through, Nmap, and we'll analyze the traffic with Wireshark. So with TCP, first of all, I'm just going to perform what you call an Nmap connect scan, right? So I'll just say ST, that is a connect scan, that denotes a connect scan, and I'm just going to connect or perform a scan on my router, right? And when I'm doing this, I'm just going to open up Wireshark, right? And I'm just going to say, okay, capture that traffic, and I'm just going to perform the scan, and you can see it does it really quickly, right? So if I just let me just open up my main toolbar there, and let me just stop the scan. Let me enlarge this, and I'll actually explain what's going on. So again, I can just click on a random packet that is being sent from my device. So I'll just go all the way to the top here from the earlier IPs being sent. So let's look at one from my device. So this one, for example. So if I just bring this window up that actually shows a summary of all the layers, you can see that if I go and I click on the transport layer, you can see we have the transmission control protocol. And now we can take a look at the header, right? So these are all the fields within the header. As I mentioned, we have the source port, we have the destination port, right? We then have the sequence number, which again is within the header, but I didn't want to explain that there. So the sequence number is very important, as I said, when sending data in an orderly fashion. It allows your computer to rebuild a packet because it's in the form of sequence. So for example, if I want to send a large chunk of data using TCP, TCP will break it down into maybe like 4 or 5 packets, and it will sequence them so that when it reaches its destination, they can be put back together into that large chunk of data. So you can see the next sequence number is set to 1 and the acknowledgement number is set to 0. But for now, you can just take a look at the header here. So this is the header. When we start talking about the flags are what we're going to talk about in the next section when we talk about TCP flags. But the important thing to take a look at here is your source and destination port, and then the flags we'll take a look at later. So that's a transmission control protocol. So we're using TCP. Let's perform an Nmap UDP scan, right? So we're just going to perform the same scan on our router, but in this case we're going to look for we're going to scan for UDP services on UDP port. So again, to perform an UDP scan, we just say Nmap and we use SU, so lowercase s and uppercase U, and I'll run this again on my router 192.168.1.1. And I'll open up Wireshark one more time, and I will just start the scan here, and I will start the capture on Wireshark, and we'll just give that enough time to perform a scan, and I'll stop the scan there. So immediately you can see now with Wireshark, the scans and the types of packets and the type of protocol being used will change the color. So in the case of TCP, we had a red color. With UDP, we now have blue. So again, you can look at the source and destination IP. You then have the protocol being used. In this case, it's UDP. So if I click on a sample packet here, I'll just click on one there, and we take a look at the transport layer. You can now see the transport layer says, hey, this is using UDP, or the user datagram protocol. And as I already mentioned, there are only two fields within the header that are important, and that is your source port and the destination port. As I said, we don't have any particular flags within the user datagram protocol. So as I said, a good example of this is when you're live streaming, or when you're making a video call or an audio call through the internet, the UDP would typically be employed there because it's connectionless. There is no sequencing of data. Data is just being sent constantly, and it's much more better for low latency types of connections if you want a much more speedier and low latency connection. So hopefully that explains the transport layer in depth. As I said, we're going to be focusing on TCP now quite a bit, because I want to talk about TCP header flags, which are very, very important with Nmap, because they determine what requests we send, and then the responses we get are then interpreted by Nmap in specific ways. So it's essential to understand TCP header flags if you truly want to utilize Nmap to its potential. That being said, that is going to be it for this video, and I'll be seeing you in the next video. Welcome back. In this video, we're going to be taking a look at TCP header flags, and we'll then take a look at the TCP through handshake, where I'll actually take you through the entire process using Nmap and Wireshark, and we'll be able to see the actual TCP through handshake take place. That being said, let's get started with understanding what TCP header flags are, arguably one of the most important sections of this particular module. So TCP header flags, or TCP flags for that matter, are found in the TCP header and are responsible for the transmission and flow of packets across the network. Now, port scanning with Nmap involves the use of specially crafted TCP flags in packets to determine the target's operating system, their service versions, and to check for the presence of packet filtering or a stateful firewall. So with Nmap, you typically, when conducting a various types of scans, Nmap will use all of these TCP header flags this will be sent to the target, and then based on the response Nmap gets, it's able to come to a conclusion. So let's start off with the first TCP header flag, which is the urge or the urgent flag, and this essentially tells the target or the recipient that the packet needs to be processed immediately, right? We then have the push flag, which again transmits the data immediately. You then have the fin or the finish flag, which again essentially closes a connection or completes a connection. This will all become apparent as to how they're used as when we take a look at the TCP three-way handshake. You then have the ACK, right? The ACK header flag, which is, again, you'll be seeing it quite a bit, and this stands for the acknowledgement, right? So this very simply acknowledges the receipt of a packet. You then have your SYN or your synchronization header flag, which initializes a connection between a host and a target. And then you have the RST, again, one that you'll be going through quite a bit. RST stands for reset, and this essentially resets the connection. All right, so you might be saying, well, yeah, that's cool, but how is this used? Well, that's where things get really exciting, and I'll be able to demonstrate this with Nmap in a second. But before we do that, let's take a look at an important aspect of TCP, and that is the TCP three-way handshake. Now, in the previous video, I mentioned that TCP is a connection-oriented protocol, in that you need to establish a connection between a host and another host, or a client and a server, or you need to establish a connection between two devices before you can start sending data. All right, so as you can see here, the TCP three-way handshake is a method used in a TCP IP network to create a connection between a local host and a server, right? So you're connecting two devices, or you're trying to initiate a connection between two devices. So the host, one host that wants to connect to another host, or a client that wants to connect to a server, the client will send a SYN there, right? They'll send a packet with the TCP header flag set to SYN, all right? And the host, so again, that means you're trying to initiate a connection. So the server or the recipient will receive the SYN, and then we'll send a SYN ACK, right? So it's not going to send a packet with the TCP header flags set to SYN ACK. So again, SYN ACK, so it receives the actual initialization, and then it acknowledges the attempt to establish a connection, and then the client, the initial client, will then receive the SYN, right? And he's then going to send an acknowledgement, right? And the acknowledgement is then sent back to the server, and you can actually go through the description here. So the client initiates the connection by sending a packet to the server with the SYN flag. The SYN flag tells the server that the client is trying to establish the connection. The server responds to that client with a packet that has both the SYN and ACK flags. The server acknowledges the connection, so that means it acknowledges the attempt to connect, and then the client receives the SYN ACK flags and sends a packet with the ACK flag back to the server, and the TCP connection is established. And then when the connection is closed, an RST packet will be sent either from the server or the client, and that will reset the connection. All right, so that is how a TCP three-way handshake works in principle. But how it's much more exciting to view this through Wireshark, and we will actually be performing an Nmap TCP connect scan that actually performs the TCP three-way handshake. So as I mentioned, we're going to be performing a connect scan. So to perform a connect scan with Nmap, and we'll be taking a look at this type of scan in the next module. So we say Nmap, and we use a lowercase s and then uppercase T, and then we specify a target. So I'll just specify my router IP for the time being, right? And I'll open up Wireshark so we can actually capture this, right? And I will just initiate the connection here, and I will start the Nmap scan. I'll start the Nmap scan, and I'll open up Wireshark, and let's see if we're able to capture traffic. So we'll just wait for that to begin. There we are. So the scan completed. I'll just run one more time. And there we are, we're able to get the packets. All right, so we can see it's highlighted in red, which means we get various TCP packets, right? So we will go all the way to the top of these requests. So right over here, and initially we have the initial SYN being sent. So there we are. We can see we have a SYN request being sent, right? So we're trying to initialize a connection with the router, and then the router will. Those are the earlier ones, but let's look for a SYN ACK sent back by the let's look for a SYN ACK sent back by the router. So we'll just search for that right over here, because we're all getting resets, right? So we get SYN So let's see, SYN-ACK, there we are, we get our first SYN-ACK, so there we are. And the SYN-ACK is being sent from the router to us or our Kali machine. And then again, you can see that we respond with an ACK, and then the connection is established. And then because the connection is closed, or the three-way handshake is then terminated, we can see we get an RST and an ACK, right? So you can essentially view the entire TCP three-way handshake. And if I go back to the earlier SYN request being sent here, and we take a look at the TCP or the transport layer, and under TCP, you can see we have source and destination port. We then have the sequence number, and then we have our flags, right? So the flags tell you that the SYN flag is being set. And then again, we can then go back to our SYN-ACKs back here. So the SYN-ACK, you can now see that the response is from the, if we take a look at the internet protocol, the response is from the router, so 192.168.1.1, and the destination is the Kali box. So you can see it's a SYN-ACK, and then we send back an ACK here. So there we are. We click on the ACK, and the flags are set to ACK there, and then the connection is reset here after the TCP three-way handshake is established. So you can actually view the TCP three-way handshake using a traffic analyzer like Wireshark, and using an Nmap scan like the TCP Connect scan. The TCP Connect scan will initiate or will complete the entire three-way handshake, and based on the responses it gets from the server, it will be able to determine as to whether a port is open or closed, and it does this for the entire list of ports or the ports that you specify. This will all become clear and apparent when we start taking a look at various types of scans and port scans. All right, so that's going to be it for this video, and I'll be seeing you in the next video.